Okay, so we're back and we're still working on the same problem. This is part 2. And in the last video that we made, we were talking about a standard problem where you have a block that's on a surface and you're pulling it with a rope at an angle. The fact that I pull the rope at an angle leads to two things. First of all, we have a added vertical component right there that we have to consider together with the normal force. See, the normal force N has to add with this vertical component that we just figured out from the force over here. So we figured out this is 100 times the sine of 30. So this guy up here vertically is going to be 100 sine 30, which is 50 newtons. That adds with the normal force in order to balance out the weight, which we said was 98. All right, so when we do the little bit of algebra here, the normal force was 48. Once we have the normal force, now we could calculate friction, because friction is always this coefficient, which is some constant less than 1, times the normal force. So we found out the normal force, we plug that in here. We got mu k, which was given earlier, as 0.2. We figured out the force of friction was 9.6, and then we just had to be clever enough to know that friction's going in the opposite direction to the motion. So we added this friction vector over here of 9.6. So the vertical forces, the up-down forces and vectors cancel out because there's no motion up or down, so they're balanced, they're in equilibrium, they all cancel each other out, and the only thing that we're left with is the frictional force and the horizontal force component of the rope. So the net force then is going to be the sum total of the remaining forces, which is just the rope and the friction. Friction goes the opposite direction, that's why we've got a minus sign on there, and we find the net force is 77 newtons to the right. Okay, that's our net force. Now, can we figure out the net work? Well, the net work is going to be the net force times the distance or the displacement that net force acted along parallel to the displacement. Now in this case I don't have to worry about the cosine of theta factor within to calculate work, because the net force is in, let's see, the net force we said is in this direction, and the displacement, as a matter of fact, this is D. D is in this direction, the net force is in this direction, so when you have two forces in the exact same direction, I mean, sorry, not two forces, but a force and a displacement or motion in the same direction, the angle between those two vectors is 0, and therefore the cosine of 0 is always 1, and you don't have to worry about that times cosine factor over here. So we're simply going to say this is our network. So we're almost done. We said we were going to solve this with the work energy theorem, and here it is up here, that the network is equal to this change in kinetic energy. So let's calculate what is our change in kinetic energy. Well, we start out with an object at rest. We finish going at a velocity of 3 meters per second. So what's our final kinetic energy? Okay, our final kinetic energy is 1/2 the mass, which is 10 kilograms, times final velocity is 3 meters per second squared, minus 1/2 the 10 times the initial velocity, which we said was 0. So this Ki, which is the initial kinetic energy, is 0. This Kf is, let's see, what is this Kf? Did this before. 45 joules. So this is 45 joules. So we have 45 minus 0 is 45, so our net work then is 45 joules. So we're going to plug that into this equation right here. Our net work, which is our force times distance, has to equal 45 joules. Our net force we figured out up here is 77. So 77 times the distance is equal to 45. and then our displacement, or distance in this case, is going to be 45 divided by 77. This is all going to be in meters, and I got 0.584 meters for that. So just a little bit over a half of meter displacement. And there we got it. We solved this problem using the work energy theorem that says that the net amount of work done is the change in kinetic energy. We looked over here, we says we're starting out with an initial kinetic energy of 0 because it had no velocity, and our definition for kinetic energy is 1/2 mv squared. So v is 0, it's at rest, no kinetic energy to start. Our final kinetic energy, we said, was the 1/2 m v final squared, and that turned out to be 45 joules. So you take the difference between the initial and the final kinetic energies, you'll get 45 joules. That's going to be equal to the net amount of work done. The net amount of work done is simply the net force times the displacement. We needed to find displacement, so our net force is something that we needed to get. We got the net force by looking at our free body diagram, and we seen that when it all was said and done, we were left with the 86.6 newtons minus the 9.6 newtons. You subtract these two, you'll get the net force, and then we're in business. All right, so I hope that helped. If you understand this problem and all the intricacies around it, you're in really, really good shape. You understand then the work energy theorem and the relationship between the two and how to do it. The tricky part was, remember up here, never assume that the normal force is simply equal to the weight. That's only true if you have no other vertical forces to add up. Okay? So catch you later, and I hope that helped.